Hey guys, what's up? Today we're going to start off with doing some double integrals. Last time we talked about joint distributions for probability mass functions. So that was just for a discrete random variable or multiple discrete random variables. Today we're going to talk about continuous random variables and doing joint distributions for continuous random variables. So let's start off with talking about double integrals because that's going to be how we work with continuous two continuous random variables that are jointly distributed. So recall integral from a to b f of x dx was just like the area under the curve. Integral from a to b f of x. So it's just the area under the curve. Well, now a double integral over some region R, f of xy dA is going to represent the volume, and put that in quotes, volume under a surface. So if you have some three-dimensional space here, you have some surface. Just draw it something like this. So then the volume down here is represented by this double integral. Now volume, we use it very loosely, similar to how we used area under the curve very loosely, because we know now that integrals can represent probability. So integral f of x dx could be probability. Well, the same thing is going to be true for a double integral. It's not necessarily volume under a surface. It's going to be probability that two random variables are within a certain region. So how do we calculate? So how do we compute double integrals? For example, say you had something like integral from 0 to 1, integral from 1 to 2, x squared y plus xy squared dy dx. So how do you compute something like this? The key is you work from the inside out. Kind of like you would for order of operations, like parentheses, or what's on the inside happens first. So first of all, you work from the inside out. And then the second thing is you treat other variables, so other variables like constants. So treat other variables like constants. So to do this integral, the way that it's set up right now, this integral would be integral 0 to 1, and then we would do the y integral. So I'm going to integrate the variables with respect to y, so I get x squared times y squared over 2 if I'm just treating x squared like it's a constant, plus x times y cubed over 3 because I'm treating x like a constant. And now y goes from 1 to 2. So we just did the y integral on the inside. So you're just going to treat the other variables like they're constants. And now we plug in the bounds for y, so it's going to be integral 0 to 1 x squared times 4 over 2. Well, let me leave the x squared attached to it. X squared times 4 over 2 minus x times 8 over 3, plus, sorry. Now minus parentheses x squared times 1 over 2 plus x times 1 over 3 dx. So I'm just plugging in what y is equal to. First of all, I plug in y equals 2. I get 2 squared, which is 4 over 2, times x squared plus, and then x times 2 cubed, which is 8. So that's how I got the 4/2 and the 8/3. Now we combine everything. So this is going to be integral integral 0 to 1 x squared times 4/2 minus 3/2 plus x times 8/3 minus 1/3 dx, which is integral 0 to 1 x squared times, oops, sorry, this should be 4/2 minus 1/2, which is 3/2. X squared times 3/2, I'll just write that as 3/2 x squared, plus 8/3 minus 1/3 is 7/3 times x dx. So this will be a single integral now, and this will be the integral from, well, just do the integral, sorry, 3/2 over 2 times x cubed over 3 plus 7/3 times x squared over 2 from x equals 0 to x equals 1. And we plug in those bounds, we get, well, the 3 here can cancel, and that's the only real good cancellation, so we get 1/2 times 1 plus 7/3 times 1/2 minus 1/2 times 0 plus 7/3 times 0, which is going to be 1/2 plus 7 over 6, which is 10 over 6, which is 5 over 3. So this is what we call an iterated double integral, because we're iterating through the variables. We do the variable on the inside first. That was this y dy variable, and then we do the outer variable, which is x, based on the fact that we have a dx right there. So we work from the inside out. I'll post some links to more discussion and examples of double integrals, but this is the basic idea. You just treat the other variables like they are constants. We could have triple integrals. We could have 4 or 5, 20 variables, however many variables you want. But for the most part, we're going to stick with 2 variables in our discussions. So that should kind of get us up to speed on double integrals, at least a little bit. So yeah, let's get into the discussion now for continuous jointly distributed random variables. So today we're talking about joint distributed random variables, but the continuous side of things. So we'll start right here with x, y are continuous random variables. The joint PDF f of x, y is a function that is non-negative, and its integral over the whole real space, or the whole real xy plane, is going to be 1. So the bounds come from the xy plane. So this is always some region in the xy plane. And in this case, the negative infinity to positive infinity for both means it's the whole xy plane. So x is less than negative infinity, or sorry, greater than negative infinity, but less than positive infinity. And y is between infinity and minus infinity as well. That means it's the entire, so it's the entire xy plane. Okay, so this is a very similar condition to what we had for single variable single continuous random variable. The function was non-negative, just like it is here, and the integral over the whole real space, or the whole real line, was 1. Well, now it's just the whole real xy plane. So it's very much the same conditions. It's just we have to use a double integral instead of a single integral. Now, how do you calculate the probability that x and y are in some region A? Well, that's right here. We do the double integral over that region A, f of xy, dx dy, or dy dx. It depends on how you set up your bounds for your region A. For the most part, though, we're going to just use constant bounds. So usually for us, A will be a rectangle, meaning x will be between two values, little a and little b, and y will be between two values, little c and little d. So that's what it means to be a rectangle as far as bounds for this double integral go. So that's what we said here. If a is equal to some rectangle, then integral, or the probability that some event a is equal to the probability that x is between a and b and y is between c and d. Well, that's just this double integral right here. Y is going from, ooh, there's a typo I've never caught before. The c and d should go with y, so this should be dy, and this should be dx. So just correct that, because the y bounds need to be c and d. X bounds are a and b. Need to correct that. Okay, cool. Any questions about double integrals? Again, I'll link some videos that I've done already on double integrals to give you some more practice, but that's the general idea. All right, now example. Let's do this example. It says a bank has a drive up and a walk up service. So you can like drive through, or you can walk up inside or whatever. So X is the percentage of the time the drive up service is used out of 8 hours. And Y is the percentage of time that the walk up service is used out of 8 hours. And we're going to say X is between 0 and 1, Y is between 0 and 1. Because, why? Well, because the percentage of time out of 8 hours, well, we can at most be there 8 hours, or at least 0 hours. So 100% of the time or 0% of the time. So these X and Y variables are just percentages. That's why they're between 0 and 1. So these are just percentages. All right, so basically it's a percentage of 8 hours. Percentages of 8 hours. Now, supposedly, this function f of xy equals 6/5 x plus y squared for x between 0 and 1 and y between 0 and 1 is a PDF. Now, how do we show that it's a PDF? Well, we have to do the double integral over the whole real line. Well, we're 0 everywhere except on the rectangle 0, 1, 0, 1. So this integral right here is all we really need to evaluate. And for some practice, you can evaluate that double integral, make sure that it is 1. I'm telling you right now it is, but you just need to verify that with a computation. So verify this. Basically fill in these 3 dots. And this function is non-negative because x is greater than 0. And if I plugged in x to my function and y squared is always positive or non-negative, this would be a positive function. So we're good to go as far as being non-negative. And we've shown, well, we didn't quite finish all the steps, but I'll let you verify that the integral turns out to be 1. All right, now the example says find the probability both services are used for at most 1/4 of the time. So that means probability that x is between 0 and 1/4. Y is between 0 and 1/4. So both are used at most 1/4 of the time. That's what that means. So all we're going to do is do a double integral from 0 to 1/4, integral 0 to 1/4. And then our function was 6/5 x plus y squared. And then I'll do dy dx. So this is going to be, do the y integral first. So integrate with respect to y first. Just because that's what we have on the inside. So integrate, integral 0 to 1/4 dx is going to stay. And then 6/5 is going to be the same. But now x is treated like a constant. So if x is a constant, I would just multiply it by y if I integrate it. Plus y cubed over 3 from y equals 0 to y equals 1/4 dx. And then plug in the bounds. It's going to be integral 0 to 1/4 for x. 6/5 stays. And then we get x times 1/4 plus 1/3 times 1/4 cubed minus, and then we would get x times 0 plus 1/3 times 0 cubed dx. And now at this point I'll pull the 6/5 out of the integral because it's really just a constant, it can come out. And now I just get x over 4 plus, let's see, 1/3 times 1 over 64. So that's going to be 1/3 times 1 over 64 dx. Integrate that. Get 6/5 times x squared over 8 plus 1 over, see, 64 times 3, 180, 192 times x from 0 to 1/4. And you plug in the bounds, it's going to be 6/5 times 1 over 8 times 1 over 4 squared plus 1 over 192 times 1 over 4 minus, and then it's going to be 0 plus 0. And the decimal, this turns out to be 0.10, or sorry, 0.0109. All right, Austin, that's a great question. Does it matter which is the integral, and which is the outer? As long as they have constant bounds, as long as you're over a rectangle, it doesn't matter if you interchange them directly, like if you just swap the order of integration. Now, if it's non-constant bounds, you have to be very careful when you change the order of integration because you also have to change the bounds of integration. So no, it doesn't matter. As long as you have constant bounds, you can just change the order of integration. So if you wanted to do x first here, that's more than okay. Definitely. So I'll just make a note. Let's pull that over, make a note. Integral a to b, integral c to d, f of x, y, dy dx is equal to integral c to d, integral a to b, f of x, y, dx dy. So this is if integrating over a rectangle. if the region of integration is a rectangle. So basically, in the xy plane, your region of integration looks like this. From a to b for x, and c to d for y. So this would be your region of integration. If you have a rectangle, it doesn't matter if you just go ahead and change them. Now, if it's not a rectangle, you have to be a little careful and change the bounds accordingly. And I'll post some links to videos that do that. I'm not going to ask you to do that too much. If I ask you to do an integral with non-constant bounds, I'll probably just have you do it without changing the order. All right, cool. Questions? Good question. Now, the marginal PDF is very similar to the marginal PMF. In the marginal PMF, what did we do? We added, so for a PMF, what did we do? We said that P sub x of x was the sum over all y, P of xy. Well, now, for a continuous random variable, all we're going to do is change the summation to an integral. So the marginal PDF, right here, f sub x of x, marginal PDF. It's like if you were only considering x and you didn't care what y was doing, you would just say you have one variable, and so you would integrate away the y variable. So when you plug in the bounds for y, it effectively just disappears, and so you don't see it anymore, so it's really just a function of x. Similarly, you could have a marginal PDF f sub y, a function that only depends on y, so you're only thinking of one variable, in this case the y variable, so you integrate away the x variable. It goes away after you plug in the bounds. So it's like going back to a single PDF, and you only have one variable because you've disregarded the other variable from consideration, basically. So that's the definition. You're going to need to know these. These are extremely important. So make sure you know how to calculate them. You will still have the other variable floating around because you won't integrate it quite yet. You're just finding the marginal PDF. So the other variable, like we see here, there's an x still, and here there's a y. That variable will still be there even after you do the single or the integral. It's like a partial integration. So you basically do a partial integration because you're not doing a full double integral, you're just doing a partial integration over one variable. Okay, now find the marginal PDFs of the same joint PDF. So marginal PDF will be integral 0 to 1 f of xy dy. So that will be integral 0 to 1 6/5 x plus y squared dy, which will be 6/5 xy plus y cubed over 3 from 0 to 1. It's going to be, if we plug in y equals, well, we should make sure we know that this is y equals 0 and y equals 1. This is going to be 6/5 x, well, let me leave it in parentheses, 6/5, and then x times 1 plus 1 over 3 minus 0 plus 0. It's going to be 6/5 x plus, let's see, 2/5. Yeah, I mean, kind of. Partial derivatives are mostly symbolic until you plug in values. For our purposes, we're mostly going to be plugging in bounds for our integrals. So it's like partial integration, but you're plugging in bounds. So kind of similar. So good question. Let's see, the marginal PDF f sub y will be integral 0 to 1, because that's where our bounds are for x, f of xy dx. That will be integral 0 to 1, 6/5 times x plus y squared dx. And 6/5 comes out. If we're to integrate x, we would get x squared over 2 plus y squared. But y squared is treated like a constant, so basically I just multiply by x. And then x goes from 0 to 1. That's going to be 6/5 times 1/2 plus y squared minus 0 plus 0. And that's going to be, let's see, 3/5 plus 6/5 y squared. Now, what's the probability that y is between 1/4 and 3/4? We can just integrate the marginal PDF between 1/4 and 3/4. So this is actually the integral from 1/4 to 3/4 f sub y of y dy. Technically, that's a capital Y there. So this is going to be the, let's see, integral from 1/4 to 3/4, 3/5 plus 6/5 y squared dy, which is going to be, let's see, 3/5 y plus 6/5 y cubed over 3 from 1/4 to 3/4. And after you plug in the bounds and do all the stuff, you'll get 0.4625. So that's it's a really good use for the marginal PDF. If you only want to worry about one variable, what's the probability one variable does something, you can just basically use the marginal PDF instead of the original PDF, joint PDF. Okay, good stuff. Good questions so far, good questions. Now, this is actually going to be an example of a region of integration that is not going to be a rectangle. So if x plus y is less than or equal to 1, that's y basically less than 1 minus x. So what's 1 minus x? Well, that's a straight line with a negative slope from here to here, say from 1 to 1. So this line right here is y equals 1 minus x. X is greater than 0, y is greater than 0. But x and y are both less than or equal to 1, but also x plus y is less than or equal to 1, so y right here is less than 1 minus x. So y has to stay below this line, so this is our triangular region of integration in this example. So this is actually a triangular region. Of integration. So a little bit more involved with the bounds, but not going to be too bad, I think, in the computation. So the example really says a company sells bags of 3 types of candy, 1 pound for each bag. X is the weight of candy 1, y is the weight of candy 2, and z is the weight of candy 3. X plus y plus z equals 1 because we're selling 1 pound bags of candy. If we know the value of x and y, then z is not a random variable anymore. So basically z is going to be 1 minus x minus y. So assume that x and y have a joint PDF for the following. So it's given by the following function: f of xy equals 24xy. And we know that we're given this triangular region. So x plus y has to be less than or equal to 1 for sure. All right, so what is the marginal PDF f sub x? So the marginal PDF f sub x is going to integrate away the y variable. So we have a dy right here. So what do? We plug in our bounds. Okay, what does y do? Y goes from 0 to 1 minus x. So y goes from 0 to 1 minus x. And integrate y. So pull out the 24x because it's like a constant. So 24x is treated like a constant. So you can pull it out of the y integral. And integral of y is y squared over 2. And now we're evaluating that from 0. These are what y are going to be. So y goes from 0 to 1 minus x. Plugging that in, we just get this term right here, 1 minus x squared over 2. And simplify that, we get 12x times 1 minus x squared, or 1 minus x quantity squared. So that's the marginal PDF f sub x. And I'm not going to derive it, but you would basically need to change the bounds to show that the marginal PDF for y is also 12y times 1 minus y squared. How can we do that? Well, we could say by symmetry. This function, the PDF f of xy, is already symmetric. What you do to x, there's no difference for what you do to y because of this region of integration. But basically you could say that x is less than or equal to 1 minus y if you were to think about x going from left to right versus we said y going from bottom to top. So it just depends on how you're thinking about describing the region, if you want x or y to be integrated first. So we were looking at y, so y was bounded above by the straight line. Well, if we're looking at x first, we actually say x is bounded to the right by the straight line. And that straight line now is x equals y minus 1. And do the same integral basically, and you'll get this marginal PDF for f sub y. Again, I'll post the videos that show you how to change the bounds in greater detail. But don't worry about it too much. Now, what does it mean to be independent? Well, for joint distributed random variables, x and y are independent if and only if, first of all, in the discrete case, the PMF P of xy is just the product of the marginal PDFs. And then for continuous, the PDF f of xy is just the product of the marginal PDFs. Okay, so just the product of the marginal PDFs. If that's the case, you say it's independent. And again, just recall, what does independent mean? Independent means is there's absolutely no relationship between them. Okay, you can't say that one changes with the other. Like if you change x, how's that going to affect y? Well, if they're independent, then changing x doesn't change y at all. There's no fixed relationship between them. So let's see, any other questions so far? You know what, it's bugging me a little bit. I'm going to go back up here and do that f sub y integral just to show you how we have the bounds set up. So basically, this region can be described as y going from 0 to 1 minus x, and then x would range from 0 to 1. And that would represent the triangular region. Or if you think about x going from 0 to the line, Well, that's the line 1 minus y if you solve it for x. And then y would range from 0 to 1. So it just depends on how you want to describe the bounds. Do you want to look at x first, or do you want to look at y first? Is y bounded above by the line, or is x bounded to the right by the line? So it depends on which variable you're looking at first. Then the other variable would just go from the constants. So x is going from 0 to 1 this way. In the first set of bounds, right here. But in the second set of bounds, y is going from 0 to 1 as x goes from 0 to the line. So then f sub y will be equal to the integral from 0 to 1 minus y, 24x y dx. And that'll be 24y integral 0 to 1 minus y x dy, which will be 24y times x squared over 2 from 0 to 1 minus y. And you see 24y times 1 minus y squared all over 2, which is the same 12y 1 minus y squared. So that's the computation for f sub y. So it was just bugging me too much not to do it. So now I can continue. And are these things independent? Well, I don't think so. So f sub x times f sub y. Let's evaluate them at different points right here. So we look at f sub x at 1/4 time and f sub y at 1/4, and they're both 27 over 16 because they have basically the same format. And if we plug in the same value, it's going to give us the same number, 27 over 16. Now we look at f of 1/4 comma 1/4. Well, that's 24 times x times y, which is 24 over 16. Well, 24 over 16 is not 27 over 16 quantity squared. So basically 24 over 16 right here is not equal to 27 over 16 times 27 over 16, which means that the random variables are not independent. So they are dependent. There is some relationship between x and y. And we already know that it's that straight line. Oh, sorry. We know that it's the relationship between the PDF and the bounds. Okay, let's look at another example. This is going to be very similar to basically like a multivariable exponential distribution. We talked about exponential distribution at the end of chapter 4. This is basically like a multivariable exponential distribution. And this example says a machine has two components that have independent lifetimes denoted as x and y, both following exponential distributions with parameter lambda 1 for the first variable x and lambda 2 for the second variable y. The joint PDF is given by basically the product of the single exponential PDFs. So this would be an exponential PDF, this would be an exponential PDF. And x and y are both just greater than or equal to 0. Well, what is this region? Well, x and y are just both greater or equal to 0. That's anything that's up here in the first quadrant. So basically anything in the first quadrant, including this axis and this axis. So that's the region of integration, or that's the region of definition. Now it says, suppose that lambda 1 is 1 over 1,000 and lambda 2 is 1 over 1,200. So basically the expected lifetimes are 1,000 hours and 1,200 hours because it's 1 over lambda for the expected values for exponential. Now find the probability the machine works for 1,500 hours. So what is the probability the machine works for 1,500 hours? Well, that means both components have to work for 1,500 hours, right? So that means probability that x is greater or equal to 1,500 and y is greater or equal to 1,500. So we need both components to work more than 1500 hours. So we need both components to work for at least 1500 hours. So that's what this x greater or equal to 1500, y greater or equal to 1500 represents. Let's see. Because this is a, these are independent, because basically this definition of our PDF is an independent PDF by definition, I can say this is probability that x is greater or equal to 1500 times probability that y is greater or equal to 1500. So very similar to kind of like what we did in chapter 2 for independent events. We just multiply the probabilities. Well, the same thing is going to happen here. We can just multiply the probabilities because they're independent. So that will be, let's see, 1 minus probability that x is less than or equal to 1500 times 1 minus probability y is less than or equal to 1500. Just using the complement rule for each one. And then that's equal to 1 minus f of 1500. For exponential, we'll call it f sub x, and then 1 minus f sub y, 1500. And then we have to remember what the CDF was for exponential. Just to recall, f of x, lowercase, was lambda e to the negative lambda x, and f sub x of x was 1 minus e to the negative lambda x. So that's basically what we're going to do here. So we're going to say that this is going to be 1 minus f sub x, which is 1 minus e to the negative lambda 1, 1500, times 1 minus, parentheses, 1 minus e to the negative lambda 2, 1500. And so that's going to be e to the negative lambda 1, 1500, times e to the negative lambda 2, 1500. And then you substitute what lambda 1 and lambda 2 are. Lambda 1 is 1 over 1000. Lambda 2 is 1 over 1200. So that's e to the negative 15 over 10 times e to the negative 15 over 12. Multiply that out. I think you should get something like 0.0639. So it's not likely that your machine will function more than 1500 hours. Only 6% of the time will the machine function more than 1500 hours. So don't forget, interpretation is so important. What is it actually saying? What is the number that you calculated just saying? It's saying that 6% of the time the machine will function more than 1500 hours. So you could say, okay, out of 1000, how many would function? Well, how many out of 1000? What's 6% of 1000? It's like 60. So 60 machines might function more than 1500 hours out of 1000. So questions. Or you could even say 63 to 64. 64 machines out of 1000 will function more than 1500 hours. So 64 out of 1000 machines will function for more than 1500 hours. So it's most likely going to function for less than 1500 hours, right? So 6.4% of the time, well, that means 93.6% of the time your machine's going to function for fewer than 1500 hours. Coolio. questions? Take a little pause here. Answer any questions. Any questions? If not, we'll move on. Keep going. So just a generalization, you don't necessarily have to just have 2 random variables. You might have 3, 4, 5, n random variables. And they may all be correlated, or sorry, they may all be connected somehow. They may not all be independent. So we have to be super careful. And what we need to do is basically have an n-dimensional integral. So yeah, we're not going to worry about this, to be honest. It's independent if the PDF is really just the product of the n marginal PDFs. But I'm not going to, yeah, don't worry about this too much. But it is possible to do all this stuff for 3 variables, 4 variables, 5 variables, whatever. The integrals are much harder to do, especially on a computer, the higher dimensional you get as far as your integrals go. And then we have something called Monte Carlo methods to evaluate those integrals. And it's much more efficient to evaluate a 24-dimensional integral using a Monte Carlo method than it is to do like an iterated integral. So, or even a numerical scheme like trapezoid or Simpsons for multidimensional integrals. Okay. There is a generalization of the binomial distribution. So this is like, should be screaming discrete. Discrete distribution. It's called the multinomial distribution, or the multinomial experiment. There are n trials, each with r possible outcomes, not just 2. Each with probability p sub I, for I goes from 1 to r. Then x sub I, right here, the random variable denoting the number of trials in outcome I. So number of trials resulting in outcome I. So it could be like, okay, rolling a die has 6 outcomes, not just 2. So you could have like x1 is the number of outcomes that gave you a 1. x2 is the number of outcomes that gave you a 2, etc. Or it could be like, what's your favorite drink? Well, there are like, I don't know how many soft drinks there are. We could just focus on soft drinks. We'll just say there's like 28 soft drinks. No, there are many more than that, but we'll just say there are 28 soft drinks. Well, then x1 is the number of outcomes in your experiment, or the number of people that their favorite drink is Pepsi. X2 could be the number of people whose favorite drink is Mountain Dew or whatever. Obviously, we have to do Pepsi products here because we are sponsored by Pepsi for now. So then the PMF. So here's the PMF for the multinomial experiment. And it's n factorial over x1 factorial, x2 factorial, xr factorial. Just keep multiplying the number of trials factorial divided by number of outcomes, or with outcome 1, number of outcomes with outcome 2, number of outcomes with outcome r, times probability of outcome 1 raised to the number of outcomes for that first option. So it's very similar to binomial, but a little bit different because we don't quite have those binomial coefficients. We actually do, they're just kind of hidden right here. So, yeah, I'm not going to really emphasize this a whole lot. We'll just do one quick experiment. Multinomial experiment example. 25% of the students are from mathematics, 25% of the students are from mechanical engineering, 50% of the students are from computer science. I picked 10 students at random. X1 is going to be the number of students from math. X2 is going to be the number of students from mechanical engineering. X3 is the number of students from computer science. Well, to do this, I just use my multinomial PMF. And my multinomial PMF says just take P of 253, which is going to be, let's see, n is 10, so this is going to be 10 factorial over 2 factorial, 5 factorial, 3 factorial, times 0.25 to the 2, times 0.25 to the 5, times 0.5 to the 3. And I believe that comes out to be 0.019226. So this was P1, this was P2, this was P3. They say this is P1, this is P2, and this is P3. Well, the percentage formats of those anyway. So that would be how you could do a multinomial experiment. Any questions? Again, not going to be like emphasized a great deal, but just an example of a joint PMF in the real world, kind of extending something we did in chapter 3. Now, conditional distributions. It's very similar to conditional probability. You can think of this as like the intersection. So this right here is like the intersection of x and y. And this is just x down here. So it's very similar to what we did in chapter 2. So similar to chapter 2. This represents intersection. This is basically representing just x. So if we start out of here with the definition, if x and y are continuous random variables with joint PDF f of x, y, and marginal PDFs f sub x and f sub y. For any value of x with f of x greater than 0, the conditional probability density function of y, given that x is equal to some particular value little x, is f sub y given x. So it's a conditional PDF. F sub y given x is, or f sub y given x of some value little y given some value little x is f of xy over f sub x of x. In the discrete case, you just replace the PDF with the PMF. And then the conditional expectation, you can find the expected value of y given a particular x value, where you can just multiply by y and multiply the conditional PDF by y, integrate with respect to y. You know, likewise, so we should say likewise, f sub x given y, equal to f of xy over marginal f sub y of y, and expected value of x given y equal to the integral from minus infinity to infinity x times f sub x given y dx. So I can do all this for x given y as well. So it's just conditional probability, very similar to chapter 2. Any questions? All right, so far so good, plugging along. Like I said, I don't know how like much I really need to emphasize. Integration is like extremely important here in chapter 4 and chapter 5. So do everything you possibly can to get some practice with integration and know how to do it, what's going on, really just how to compute these integrals. It's going to be extremely important because they're everywhere. All right, example, same thing. We had above, it was like a drive up and walk up situation at a bank. X is a percentage of the time we walk up out of 8 hours, or drive up out of 8 hours, and Y is a percentage of the time we walk up. We already found the marginals. Now, what is the conditional PDF of Y given that X is 0.8? Well, what is that going to be? Conditional PDF is going to be F of Y comma 0.8 over F sub X of 0.8. So that is going to be F of XY is going to be 6/5 times 0.8 plus Y squared over F sub X we said was 6/5 times 0.8 plus 2/5. And that's going to turn out to be 1 over 34 times 24 plus 30 Y squared. So that's the conditional PDF. That's the PDF for Y if X is a certain value, in this case 0.8. So this is the PDF F sub Y if X equals 0.8. So given that X is 0.8, the conditional PDF. Conditional PDF if X is equal to 0.8. So you could say, what's the probability Y is like between 1/2 and 3/4 given that X is 0.8. So the percentage of time being used outside is 0.8 out of 8 hours. So that's like 6.4 hours. So given that the drive-up service is used 6.4 hours out of the day, what is the PDF of Y? What is the probability density function? So, cool. Now, what's the probability that Y is less than or equal to 0.5 given that X is 0.8? Well, that's just going to be integral from 0 to 0.5 of our conditional PDF Y given X of Y given 0.8. Y given that X equals 0.8 dy, which means we just integrate from 0 to 0.5. The PDF 1 over 34, 24 plus 30 Y squared dy. We get 1 over 34 times 24Y plus 10Y cubed from Y equals 0 to Y equals 0.5. And that decimal turns out to be, I think, 0.390. So that's the probability that the outside window, or the, let's see, make sure that's the walk-up. Yeah. So the probability that the walk-up service is used at most for 4 hours. So walk-up service used at most 4 hours. Walk-up service used at most 4 hours, given that the drive-up service is used 6.4 hours. So that's what this probability is finding. The probability that the walk-up service is used at half the 8 hours, so that's 4 hours, at most 4 hours, given that the outside or the drive-up service is used 6.4 hours. So 39% of the time, you're going to go at most 4 hours on the inside and 6.4 hours on the outside, or the drive-up service. If we were just looking at the marginal PDF, like we just want to know what's the probability that the outside service is used, the walk-up service is used 4 hours. So this is just a probability. In general, probability that walk-up service is used at most 4 hours in one day. That would just be the integral from 0 to 0.5 of f sub y dy. And we have to remind ourselves what was f sub y. It was equal to, let's see, that was going to be 6/5 y squared plus 3/5 dy. And that's 6/5 times y cubed over 3 plus 3/5 times y from 0 to 1/2. And you work that out and you get 0.350. So if it was independent, if these two variables were independent, the walk-up service and the drive-up service, if they were independent, then we should get the same thing no matter what x is, but we get a higher probability that people use the walk-up service given that the outside service was being used 6.4 hours. So these would be not independent because, so since probability that y less than or equal to 0.5 is not equal to probability that y less than or equal to 0.5 given x is 0.8, these x and y are dependent. Otherwise, if they were independent, these would be the same. It shouldn't matter what x is if they're independent, but it does matter. X being some particular value does change what happens to y, so they are dependent. Very similar to what we talked about with probability in chapter 2. So again, just take a second, think about it. If you have any questions, now's the time to ask. All right, so if we were to calculate the marginal, the expected value of y just by itself, normally we expect to use the walk-up service 0.6, or let's see, that'd be 4.8 hours out of the day. So basically this means we expect walk-up service to be used 4.8 hours out of 8 hours. So that's what this expected value tells us. It's telling us how much time we expect the walk-up service to be used out of 8 hours. So 4.8 hours basically. Now, given that x is 0.8, how much time do we expect to use the walk-up service? Well, we expect to use walk-up service just a little less than 4.8 hours. So I'm going to punch that in. So 0.574 times 8 is 4.592 hours, 4.592 hours out of 8 hours, given that the drive up service is used 6.4 hours. Out of 8 hours. So don't forget, what is x? What is x? What's y? Well, the values for x and y are the percentage of 8 hours that the service is being used. So because these expected values are not the same, you can say the random variables again are not independent, they are dependent. So x and y are dependent. I mean, think about it. If you have more customers outside, you probably have more customers inside. Furthermore, if you have more customers in the drive-through, people are going to be like, oh, I don't want to go through the drive-through, I want to go inside. So it's just like an overall, like the more customers you have overall on the outside, you probably have that many more customers on the inside. So these definitely are dependent random variables from our computations, and then just thinking about it logically, we could kind of see that that would make sense if this were actually a real model, a real function to calculate that. Okay, now expected values. So the expected values of functions right here, expected value of a function, h of x, or h of x and y, depending on if it's discrete discrete or continuous. It's pretty much the same game. The game is we just multiply the function h by the probabilities in discrete case, or we multiply the function h by the PDF in the discontinuous case and integrate. So it's kind of the same thing that we've done, just we have a double integral or a double sum versus a single integral or a single sum. But yeah, pretty much the same thing. So 3 types of candy, like we talked about before. X is the weight of candy 1, y is the weight of candy 2, z is the weight of candy 3. The function, the probability we said was PDF 24xy, and it's a triangular region. And the total cost of a bag is the, let's see, candy 1 is 1 times however much is in x1. Cost of candy 2 is 1.5 times however much is in candy 2. And then cost of candy 3 is 0.5. So we'll say like $1 per pound, $1.5 per pound, and $0.50 per pound. So it's like $1 per pound. This is like $1.5 per pound. This is 50 cents per pound. So what can we do? Well, we know now that z is not independent. It's definitely dependent on x and y, because the total sum x, y, and z has to be 1 up here. So basically just take that, solve for z, and stick it right there. And now this function, the total cost function, this is the total cost function. Total cost function. We can find the expected cost of a bag of candy. So that's exactly what this right here is. So expected value of this function, the total cost function, is going to be the double integral of the function. And this is our function, h of xy times 24xy. That double integral, once you do it all, you plug in the bounds. Notice we put in the bounds. We're doing y first. Mistake here. This should either, we'll do y and then x. Oh, frustrating. Can't believe I haven't seen these before. All right, so this is the cost of a bag, $1.10. Make sure you just note that these changes right here should be a y, because they're doing y first based on their bounds. And then this should be x. So dy dx. You do that integral, you get $1.10 per bag. That's the expected cost of your bag. Cool. Questions? Nada. No questions so far. That's good. Let's see. Covariance. We'll have to start here next time. So next time. So we are out of time for today. So we'll get through covariance next time. Correlation and all that next time. And then we'll just about be done with chapter 5, I believe. So next time is actually going to be next Wednesday, right? We don't have class this weekend or Monday. We're going to have class next Wednesday. So we'll see you again on next Wednesday. I'll hang out again just for a few minutes if you have any questions. If not, have a good weekend, long extended weekend, and stay safe. Have a good one.